So here we go with session number 2 after, I think we all agree, a fantastic start off with James Heathers. We're going to move straight into abstracts now, which I think thanks so much to the guys who submitted. Some really great projects here. We've got Chris, Jenny, Simon, Brad, Christian, Gabriel and David. Some really fantastic projects, and I think very nice balance now, going from all the problems and everything's wrong in science into solutions and moving forward. So the way we were hoping for this to work is that everyone who submitted an abstract is just going to take 5 minutes to give a brief overview of that abstract. They are all available on the STORK Summit website right now. I see Vanessa's sharing the link there in the chat, and the contact details are there too, because obviously within the bounds of this particular session, it'll be a very brief overview. We won't have a huge amount of time to get into the details, but at least it'll give us all an idea of what's going on. And as I mentioned before, we have that kind of specific project room. We've put the presenters' contact detail alongside their abstracts. So I'm sure I can, well, I hope I can speak on behalf of the presenters that you're okay to perhaps follow up with questions if we don't get time to do it all right now. So without further ado, Chris, sample size justification in gait and posture. Chris is coming to us from Maastricht University, major STORK advocate, and I'll shut up now. Chris, thanks a million, go for it.
Yeah, can everyone see and hear me on the screen? Yeah, okay, great. Yeah, well, thanks for the quick introduction. So I'll give a brief overview of this project that me and a few others in my department did last year. Yeah, for those that don't know me, my main area of research is in, well, walking biomechanics and fall prevention. And for that, one of the kind of core journals is the journal Gait and Posture, just for some context. Now, when I was preparing a submission for Gait and Posture, and I noticed this quote in the author guidelines, which is that all articles should include the justification of their sample size. And I knew myself from a submission a few years previous that this hadn't always been there. And I also then saw that this was supported explicitly by 2 editorials, from the editor-in-chief and from the journal's statistical editor. And I later found out that this guideline was not in place prior to May 2018. And it was in place at least from the 25th of July 2019 onwards. And so being interested in, well, improving science from all different aspects, I thought, okay, well, this is actually a nice opportunity to look at the impact of including a relatively simple statement in the author guidelines. So yeah, me and a few colleagues got together, and how we did this was we did an audit of sample size justifications in, well, for time and resource reasons, the 3 most recent journal volumes at the time that we did the project, and the 3 most recent volumes of the journal before the guideline was present. So this was 324 articles, 176 pre and 148 post guideline. And in order to classify and categorize the justifications present, we used Daniel Laken's, at the time preprint, it's since been published as an article on sample size justification. And this table, you can see the kind of common justifications for sample sizes that he suggested. And we added our own category of a combination of these or an unclear justification. So just briefly, the main results, you can see on the graph on the left, the number of articles on the y-axis, pre-guideline, post-guideline are the 2 bars. And well, the one thing that we were really interested in was, do sample size justifications change? And they do. There's a modest increase from the rather disappointing 16.5% up to 28% with the inclusion of this guideline. You can also see that the articles without justification decreased, and there was a slight increase in unclear justifications. And perhaps for those in a similar field to me, not surprising that the most common category was an a priori power analysis. There wasn't much consideration of any of the other types of justification. And of the 324 articles, only 1 article mentioned resource constraints, which I thought was interesting. So the brief conclusions, the guideline, as it was presented in the journal Gait and Posture, obviously was not a consistent criteria for publication enforced by the journal or publisher. As a reviewer for this journal, I can also say I was never specifically directed to pay attention to this, even though it was already in the guidelines. The guideline was associated, we can't infer causality, but it was associated with a modest increase in the rate of sample size justification reporting. But obviously, this is not a guarantee that the justifications are appropriate or of high quality. And as you can read in the article, we actually found most power analyses were not reported in sufficient detail to replicate. They usually depended on single, often pilot studies for their effect size estimate. And smallest effect sizes of interest or clinically meaningful differences were very rarely mentioned. So that gives you a small taste. And well, you can see the full publication and also the materials and data at the links on the screen. So thanks very much.
Awesome. Thanks so much, Chris. Guys, I'm going to suggest that we just go one after the other, and then we'll do as many questions, discussions as we have time for. So thanks a million, Chris, for kicking us off. Next, we go to Jenny Murphy from Dublin, who is going to talk about her project on attitudes towards and perceptions of reproducibility and replicability in sport and exercise science. Thanks a million, Jenny.
No worries, just get myself sorted. Can you all see my screen? Yeah. Okay, so hi everyone. As Emer said, I'm a PhD student based in TU Dublin in Ireland, and my research focuses on replication in sports and exercise science. So as part of this research, we conducted a survey whose aim was to explore the attitudes and perceptions of active researchers towards reproducibility and replicability in the field of sports and exercise science. So for the methods for this study, we adapted a study from Nature with permission from Baker in 2016. And then we accessed the freely accessible corresponding email addresses of sports and exercise science researchers on the Web of Science database. We then analysed our results using our software, and we also used a thematic analysis for the open text box responses. So in total, we had 511 responses to our survey. And one of the key findings was that almost 43% of the respondents believe that there is a significant crisis of replication in sports and exercise science, while almost 36% believe there is a slight crisis. Then when answering a question on the factors that they believe contribute towards poor replicability and reproducibility, they stated that selective reporting, insufficient mentoring, publishing pressure, and poor experimental design were among the highest contributing factors. So as I mentioned, we also conducted a thematic analysis, but just for the purposes of today, I'm going to present a very small selection of the quotes. The first theme that was apparent in the thematic analysis was research culture. So there is a current consensus that engaging in open science can be detrimental to career progression, and that there are no incentives in place to actually conduct replication studies. There simply is no individual benefit, and in fact, you'll probably get behind in your own publications, so it may even be detrimental for your career. The respondents within the field are also very frustrated with the journal and publication system. They believe that their focus is on the impact factor, readership, and profit. Publishers are leeches who care nothing more than making a profit. Token gestures of encouraging open access and data deposition are hollow at best. They do not help. The second theme that was identified was statistical education. And there was a belief among the respondents that statistically naive editors and peer reviewers can be a barrier to reproducible and replicable research. The peer review process is only as good as the peer reviewers. Many reviewers miss issues within methodologies. However, researchers also feel that the overall statistical expertise within the field is really substandard and potentially causing a high volume of errors. Researchers believe that they know more about research than they do, making serious errors in methodology, using the wrong statistical tests, or not having clear objectives they know how to accomplish. So the third theme was a research responsibility, and many of the respondents felt that journals have too much responsibility within the research process. Journals are gatekeepers to much of what we publish as scientists. We are bound by their rules. So obviously journals can facilitate open science practices via author guidelines, and they can also enforce reporting criteria. But publication is also the last stage of the research process. So should we as researchers be doing more? We seem to be complacent with the status quo of low sample sizes, poor description of methods, and publication bias towards novel findings. Frankly, it makes us look bad. The final theme in our thematic analysis was the current practices promoting replicability and reproducibility. So a lot of respondents feel that journals do have checklists in place to try and to try to improve replication and reproducibility in the field. However, these checklists are too generic. There's no standardization or enforcement of them. Journal checklists are overly generic, which impedes their utility. Making them more extensive is not useful and would drive me crazy, especially for a DES reject. So obviously, based on the results of our survey, there were some key areas to focus on for reproducibility and replicability within the field. So the first one is that we should undertake a collective effort to support journals who promote open science practices and guidelines rather than a focus on profit, and that we could also make better use of preprint service to try and avoid the file drawer effect. The second recommendation was to potentially introduce pre-registrations or registered reports, or even replication studies as part of class research projects or PhD studies. This would help to promote statistical education, but also it would give the students a better understanding of the importance of clarity and transparency in their work. And then finally, the researchers feel that we, within the field of sports and exercise science, need to assume increased responsibility for the replicability and reproducibility of our work. We shouldn't expect improvements to be made to our research designs during the peer review process. Therefore, we must design our studies appropriately, power them appropriately, pre-register them, conduct pilot testing where possible, and also make our code or data available afterwards where possible too. So that was just a quick synopsis of the survey and the results we conducted. Happy to answer any questions, and thank you for your attention.
Brilliant. Thanks so much, Jenny. Great recommendations to finish us off there. Spiral and or package for reproducible and tests. Simon is here. I saw him. Oh yeah, there we go.
Yeah. Thank you very much.
Thanks, Simon. Over to you.
Okay, I believe it's not always the incentives that lack when it comes to reproducible research in sports and exercise science, but sometimes it's simply the lack of appropriate software. And that's especially true for the field of cardiopulmonary exercise testing, which is quite common in sports science, especially in exercise physiology or in training science, to investigate gas analysis parameters or heart rate responses to exercise. And in this field, there's a lack for appropriate, easy-to-use software that allows for standardized processing of raw data. And this is a reason why I designed such a software within the R environment. And it's called Spiro, and I'll just show a brief demo of it. So it basically allows you to import data, different raw data files from metabolic cards, and it outputs you a summary with just one line of code. Or you can go on and create like maximum parameters. So like the VO2 max, there's also simply a one-liner of code. And it's not only easy to use, but it's also quite fast, working within a fraction of a second to produce its outputs. And so the basic functionality is that it supports many different metabolic cards. So that is a standardized way of processing for different types of devices. It allows the processing of data you've just seen here. It allows data summaries to calculate data summaries. It offers functionality for plotting, like the Wasserman 9 panel plot you saw on the first slide, also created by this package. And there's much more to explore, like different filtering methods, support for external heart rate data files, automated guessing of exercise test protocols. Much more you can see. So I'll just refer you to the webpage for the software. I'll later write the link in the chat too. This software is still under development, but it's come quite far. What's next is that it will undergo a peer review, so a software peer review, a process that will start in the upcoming days. I also plan to support as many different devices, as many different metabolic cards as possible. And that's especially a point where I need your help. So if you want your metabolic card to be supported by the software, feel free to send me some raw data files, some example data, so I can incorporate this the support for them. You'll find my mail address on the webpage for the abstracts or on the package website. And as I'm aware that unfortunately not all of us and not all of sports scientists in general are users, I may plan to make the functionality of the package accessible for all others by turning it into a website. But in terms of reproducibility, that would at least that would only be possible if the website is at least code generating to allow for reproducible analysis after that. So that's something that's up for the future, and I'm looking forward for that. And I'm always grateful for help, especially in terms of these upcoming development stages. So thank you very much for having me. I look forward to you. I invite you to test this the software. I invite you to give me your feedback, and of course to send me your raw data files. Thank you very much.
Awesome. Thanks so much, Simon. That looks like it could be a massively useful package with a lot of applications. And again, just to reiterate, everyone, feel free going in the chats. Any questions? We're not going to stop right now. We're going to move on to Brad McKay from McMaster University. It's just occurred to me as well, we've gone from the Netherlands to Ireland to Germany to Canada. Nice to see that we're fairly international today. But thanks very much, Simon, and Brad, over to you.
Great, thanks a lot. So yeah, my presentation is about basically the rate of positive results that we see in motor behavior research, and then the application of a couple different tools that can be useful for trying to control those error rates. All right, so just to sort of set it up, I'll show you some results from a kind of a trivial simulation study to be fair. But what we did is we simulated a traditional motor learning experiment, which is the field that I primarily work in. So we imagined, you know, somebody's practicing throwing darts. So we can simulate some raw data from this person throwing darts, and we can simulate that over time. So they would practice in many experiments. They might practice in 5 acquisition blocks and then have some sort of break, usually like 24 hours, and then come back and do a retention and a transfer test. So we can simulate those data sort of correlated over time. And then we can calculate traditional error measures for these outcomes. So like the accuracy, how far they were from the bullseye, the dispersion, the type of spread in their darts, the bias, were they missing left, were they missing right? And then go ahead and simulate a bunch of experiments based on these individual data sets. So we chose 17 participants per condition, and we simulated like a 2x2 factorial design. And the whole idea here was just to illustrate the type 1 error rates that you'd get if you had no error control whatsoever, and you just analyzed a traditional motor learning experiment with traditional analyses that use a bunch of different varieties of analysis of variance tend to get used in this field. And without any error control, and like I say, it's pretty trivial because if you just add up the 0.5 error rates, like this is what you get roughly, but you get really high error rates. And so the issue then is in trying to control type 1 error is it's grounded in what hypotheses you're testing. And so one way that could be useful for controlling type 1 error by specifying the primary outcomes of interest, or specifying how multiplicity will be handled with multiple, based on multiple comparisons, is to use pre-registration and say up front, this is the outcome I'm interested in, and this is how I'll correct for multiplicity. So to investigate the extent to which pre-registration is being used in motor behavior, we did a review of all the studies that have been published in 3 motor behavior journals over a 2.5-year period. And the criteria to be included was that the study had to be sort of a primary empirical study, and it had to include a hypothesis test. It had to be testing some prediction. And in the end, we found 636 individual studies that met this criteria. And so the first question was, you know, how many of these were pre-registered? And the answer was not very many, 4 were pre-registered. So that's fine. Part of the idea here was to investigate how much room is there for improvement to maybe the existing status quo if there were to be increased adoption of pre-registration. We also asked, were the pre-registered studies less likely to report support for their hypotheses than the non-pre-registered studies? And of course, we only had 4, so take this as it is. But the answer was yes, they were less likely. Only 1 in 4 of the pre-registered studies found support, whereas like 85% of the non-pre-registered studies found support for their primary hypothesis. So another type of error that we can get in addition to type 1 error is we can also have false negatives where perhaps we have underpowered studies. And certainly in the motor learning sphere, there's been a few papers that have raised this as a potential issue. And one way to control false negatives or type 2 error rate is by conducting an a priori power analysis. And so we looked at, in the same literature, what's the frequency of a priori power analyses in the motor behavior literature. And as you can see, it's more common than pre-registration, but still not particularly common. Only about like 13% of studies included a priori power analysis. And then we asked again, does the frequency and support change? And not really. The studies that included a power analysis were actually a little less likely to find support for their hypotheses than the studies that didn't include power analyses. Wasn't a significant difference though. And so, you know, the general conclusion from this is that as a field in motor behavior, we're not currently using pre-registration or power analyses as tools that can be used to control our type 1 and type 2 error rates. And so that means that there's room available for improvement to benefit the field by adopting these practices. That's all I got for you. I'd like to thank my collaborators, and including the camera shy ones. And that's it.
Awesome. Thanks so much, Brad. One thing I'm loving about all of these is how they go between different places. Straight away, I'm thinking, oh, I wonder what that would look like for sports nutrition. I'm guessing probably not very positive, but maybe we'll be trying to replicate your study in another discipline. We'll keep going on because I'm conscious of time, but next up we're heading back to Ireland, back to Dublin, and Christian.
Yep, hi. Can you hear me?
Yep, can hear and see you good.
Okay, perfect, thank you. Okay, so yeah, my name is Christian, and I'm a PhD student at TU Dublin investigating the replicability of sports and exercise science. Over the course of this presentation, I'm going to talk about the replicability of a set of studies published in the Journal of Sports Science. Oops, sorry. Okay, now. Okay, so in an ideal world, we would assume that researchers formulate and test specific hypotheses, pre-register studies, and conduct a priori power calculation for sample size planning. Researchers would also collect data based on the priori power calculation conducted beforehand and analyze data usually using pre-specified statistical tests. Researchers would also interpret data carefully, and finally studies will get published regardless of whether a statistical significant effect was found or not. However, in reality, researchers test vague hypotheses, do not use pre-registration nor pre-study power calculations, and consciously or not, researchers use flexibility in data analysis searching for significant p-values. Finally, studies claiming for statistical significance are more likely to get published. Consequently, the presence of these issues distorts the research process. In the field of sports science, it has been observed that about 82% of the studies supported research hypotheses, indicating that an overwhelming portion of the studies reported a significant p-value. For biomechanics and sport science journals had a sample size of 22 participants, which may indicate the presence of studies with underpowered designs. And it has also been observed a lack of replications in our field. Similarly, in the Journal of Sport Science, it has been reported a median sample size of 19 participants, and only 12 out of 120 papers used a priori power calculation. The previous findings may suggest that the presence of publication bias and studies with underpowered designs in our field. The consequences of these factors are likely to be an inflated type 1 error rate and an overestimated effect size, which ultimately will decrease the replicability of any set of studies. So the question is how we can, with sport science researchers, detect the presence of publication bias and studies with underpowered designs. One way is the zeta curve method that meta-analyzes the p-values from individual studies. Basically, zeta curve transforms observed p-values into zeta scores. Zeta curve analysis use a mixture of normal distributions centered around or at mean 0 to 6 to fit a model of the underlying effect size that best represent the observer results in the included studies. Overall, the zeta curve aims to estimate the average power of a set of studies and the presence of publication bias. In an unbiased literature where the null hypothesis is true, we should observe approximately 5% significant results. If the null is true, the distribution of zeta scores is centered on 0. Then zeta curve computes absolute z-values, and therefore 5% of the zeta scores observed should be larger than the critical value, 1.96 for the significant or for the 5% alpha level, as indicated by the red vertical line. In the figure, zeta score for 1,000 studies are plotted with a true effect size of 0, where exactly 5% of the observed results are statistically significant. However, if there is a true effort, the distribution of zeta scores shifts away from 0 as a function of the statistical power of the test. The higher the power, the farther to the right the distribution of zeta scores will be allocated. So we used a study selection protocol based on the protocol of my colleague Jennifer Murphy. Any study in order to be included in the zeta curve analysis had to be an applied study published in the Journal of Sport Science, follow an experimental or quasi-experimental design, report either a t-test or an f-test, and report the exact p-value or enough information to recompute it. 523 studies were screened, of which 349 were excluded. Then 174 were assessed for eligibility, of which 55 were excluded. Therefore, we ended up with a sample of 119 studies, which were included in the zeta curve analysis. Here we can see the distribution of the 119 zeta scores and both the power and the publication bias estimates. The observed discovery rate was 0.69, indicating that 69% of the studies reported a significant finding. The expected discovery rate was 0.48, which indicates that the average power of all the studies with both significant and non-significant results, and the expected replication rate was 0.60, which represents the estimated proportion of significant studies that would yield another significant effect if subjected to a direct replication. Then we should pay attention to the file drawer ratio and the estimates of the observed discovery rate and the confidential interval for the expected discovery rate. The estimate of the observed discovery rate, which was 0.69, lies within the 95% confidential interval of the expected discovery rate. This suggests that even though there is a discrepancy, there is not enough data to statistically reject the hypothesis that there is no evidence of publication bias. However, the confidential interval was rather wide due to the small sample of studies included. A visual inspection of the obtained results suggests that there is a potential indication of publication bias. As you can see, there is a steep drop from just statistically significant values compared to with non-significant values. Another additional point of evidence to support this contention is that the failed error ratio has a point estimate of 1.1, and this indicates that the ratio between published and unpublished literature is approximately even. This means that for each published study result, there is on average 1.9 non-significant results in the file drawer. To conclude, based on these findings, there may be an excess of significant findings given the observed presence of publication bias and underpowered designs. And then it's likely that a portion of published findings cannot be replicated to the above practice, which are likely to increase the number of false positives and produce overestimated effect size. Yep, that's it.
Brilliant. Thank you so much, Christian. So
Thank you.
kind of disturbing data in there, but luckily we're all here searching for solutions. So let's see what would happen if you repeated this in 5 to 10 years.
Yeah.
We're going to go now from Ireland to Brazil. And next up we have Gabriela Esteves, who is going to talk about prevalence, barriers and motivations to the use of open science practices in sport and exercise science. Guys, I'm just conscious of the time now. We're probably not really going to have much time for discussion or question and answers after this. So if you do have questions for the individual presenters, pop them in the chat now, or else maybe make a note to pop into the specific project meeting room afterwards. Because we'll try and keep to the schedule as much as possible, which of course would be easier if I was more concise and stopped wasting time talking about lack of time. Okay, Gabriel, you're up.
Yeah, Chris, I think your screen is frozen. If you could stop sharing. I don't know.
I think, Gabriel, if you try to share, you should be able to override it.
Yeah, okay, that's actually, it wasn't allowing me to share. So.
Oh, right, sorry.
Perfect.
Nice.
All right, guys. So, hello, I'm Gabriel Esteves. I'm currently a PhD student at the University of São Paulo in Brazil. I'm going to be presenting to you our project. Currently, this is just the protocol, so no exciting results yet, but hopefully you'll be able to see results in the future. But we would very much like to receive any feedback that you may have concerning the methods. So the project title is Prevalence, Barriers and Motivations to the Use of Open Science Practices in Exercise Science, a questionnaire-based exploratory study. So initially, I was going to give sort of an overview of the literature and science in general, but I think James did a way better job than I could do, so I will go fast through this part. So essentially, QRPs, questionable research practices such as p-hacking, harking, the selective publication of results, they lead to a biased literature. On the other hand, open science in general and open science practices hopefully can assist us in having a literature that is more transparent and reliable, which is what we want in the end. Currently, information that we have concerning the state of our literature come from this very interesting registered report by Rosie Tomei and colleagues. So we know that our literature has very high rates of positive results and low rates of sample size justifications and pre-registration and access to open science. And so we probably would like to change that somehow. But first, we would need to understand the motivations and barriers towards the use of open science practices that researchers face, right? So that's our main goal here. We will be using a questionnaire approach. This questionnaire will be given via and sent out via Google Forms, and it will collect information on participant characteristics such as age, discipline, career stage, and job position. Also, the prevalence of use of the many different open science practices such as pre-registration, registered reports, the use of open data and open code, and preprints, among others. We'll also be asking about the perceived barriers and motivations towards each of these open practices. And yeah, essentially we would want to understand what are the perceived negative and positive aspects of each of these. And in the end, we'll be asking if the researcher thinks it's worth it to go through this positive and cons. This will be asked via both multiple choice questions and open-ended questions so that we can dig a little bit deeper. So this questionnaire is currently done, ready. It's at a good stage, but we would like to improve it. So we'll be using a Delphi scoring approach. 10 researchers will be invited to have a look at the current version of the questionnaire and score each of the questions from 1 to 10. And questions with a score of 7 or more will be approved, 3 or less will be excluded, and in between will be reformulated to improve the questionnaire. So our participants will be any kinesiology or sports and exercise science researcher. Obviously, we'll be using a convenience sample, and that comes with limitations, but we'll make sure that we highlight that throughout the manuscript and cite sort of the demographic characteristics of our population here. Our analysis will be mostly descriptive exploration of the results. So means and standard deviations for the continuous variables, frequencies for account data, and the frequency of responses of the different questions, and maybe median and interquartile ranges for some more skewed data that may emerge. Also, we plan to explore the effect of potential moderators to the responses in a few of the questions. So we basically would like to understand the role that age, job title, career stage, and discipline may have on, for example, the prevalence of use of the practices, or whether they think it's worth it or not to engage in these practices. And of course, the open-ended questions will follow a traditional exploratory content analysis. And so the relevant themes will be codified and reported. So that's it. That's the current team working on this project. And currently, we've just received approval from the local ethics committee. We plan to submit this study to a registered report in communications and kinesiology. Even though it's quite an exploratory project, we would very much like to receive feedback on that. So I think that's a good opportunity. We'll also proceed with a Delphi scoring questionnaire. So if you would like to maybe review and participate on this aspect, feel free to contact us. And yeah, after that, we'll begin data collection. Yeah, so that's it. Thank you.
Awesome. Thank you, Gabrielle. And just to reiterate that there'll probably be lots of STORK members targeted for Delphi consensus approaches. If anyone's interested, feel free to get in touch. And we're going to wrap up. Our final abstract presentation is coming from Australia. It is currently the middle of the night. So David Borg, who's going to talk about a study of statistical significance published in Sport and Exercise Medicine journals between 2002 and 2022. So he sent me his slide in advance because, as I say, it's the middle of the night in Australia. So let me just see if I can do this properly. I believe the text will come up as soon as I start. You guys seeing that okay? No, that's not what I want to do. Damn it, hold on one sec. The tab of the thing is hiding the bit where I start the slideshow, and I need to start the slideshow. I should be able to get it down here, right?
Good afternoon. My name is David Borg, and I'm a research fellow at the Queensland University of Technology in Brisbane, Australia. Before I get started, I'd just like to say thank you to the conference organising committee for all their efforts, and also to my co-authors for their contributions on this work. Sorry. Today I'll be speaking about some work we recently did looking at statistical significance in sport and exercise medicine research over the past 2 decades. Traditionally, bias in the published literature has been examined using p-values to generate p.
Sorry guys, I obviously did something stupid there. I'm seeing in the chat that you can that you couldn't see my thing. Let's try one more time. Can you see right now? Can we get sound?
And looking to see whether there's an excess of p-values just below the commonly used threshold of 0.05. The biases shown when looking at the distributions of these p-values has led to calls for the use of confidence intervals in place of p-values, in part to overcome such biases. So what we were interested in is whether confidence intervals in the field of sport and exercise medicine are subject to similar biases, p-values, at least in the published space. In particular, we're talking about confidence intervals on ratios, and by ratios we mean risk ratios, hazard ratios, and perhaps what people are most familiar with is odds ratios. So when used in practice, ratios are often reported with a 95% confidence interval, which is generally used as a proxy for statistical significance. When the 95% interval does not include the null hypothesis value of 1, researchers would conclude that their result is significant. So using a previously validated text mining algorithm, which recognizes the ways or the typical ways in which ratios are reported, we searched over 50,000 abstracts published on PubMed. Abstracts were from articles published in 18 highly ranking journals in the sport and exercise medicine space over the past 2 decades. After excluding intervals for a couple of reasons, the primary of which was not reporting the level of confidence, which occurred in 10% of cases, we performed our analysis on 3,800 intervals that came from about 1,600 articles. Bias was examined graphically using cumulative distribution plots of the upper and lower bounds of 95% intervals. And in particular, we were focused on whether there were any abnormal patterns or changes in the distribution around a ratio of 1. We compared our results to a health data set that has not been subjected to p-hacking or bias and can be considered an unbiased, a data set of unbiased results. As a final step, we also looked at the distribution of Z values related to the interval pairs that we extracted. So looking at the plot on the top right here, we can see in the left panel that the distribution in red, which is our results, has this marked change at a ratio of 1. So there's this excess of results just of lower bounds just above the significance threshold ratio of 1. Similarly, on the right-hand plot, looking at the upper bounds, we can see that there's this marked change in the distribution at 1 with this excess of results just before it. The bias in our results that we saw was further highlighted by the distribution of Z values associated with our intervals. And we can see in the dark blue here that there's this large absence of results there's this large absence of results that would be considered not statistically significant. While our findings are disappointing, they're definitely not surprising. And what they do show, though, is that confidence intervals, at least on ratios, are subjected to similar sort of biases that p-values have previously been shown to be subjected to. What we really need to do is focus our attention towards increases in research transparency, which I know everyone's here is on the same page, but we really need to increase the use of pre-registration and perhaps more importantly, the use of registered reports. And we know that these are 2 things that are particularly underused in our area, at least at current time. We encourage, based on our results, we encourage researchers, peer reviewers, editors, and also journals and their policies to focus their attention away from statistically significant results only.
Okay, I think David's, he might have cut it at 5 minutes there, but I think he was coming to the end, but that was all there was there in the screen. But yeah, awesome. Fantastic job. Thank you so much to the guys. Unfortunately, we're not going to have much time for question and answer now, but let's keep using the chat. Let's use the breakout rooms. Guys, we have a brief break now, just 7 minutes now, because we're a couple of minutes over, but I think obviously online meetings can be intense. Let's get up, stretch the legs, grab a coffee. Anyone who's free, head on into the breakout room and the general chat room or specific project if you want to discuss something in particular. And let's get ready, be ready to go again at, for me, 1 o'clock. whatever the hour, in 7 minutes. All good? Cheers.